Welcome to the lesson video on Bayesian model selection and model averaging. In this video, we're going to talk about model averaging. This is a topic that extends some of the ideas that are covered in our textbook. Model averaging is a process where we're doing linear regression with multiple variables, and we compute the probability for each linear regression model, and then we take the weighted average. As we've talked about before, you'll often get a number of different models depending on which regressive variables you choose. And then you can use AIC or BIC or some other method to pick the best model. In model averaging, we don't pick the one best model. What we do is we look at a number of good models and we compute the probability for each of those good models or each of the top models. And that gives us a probability for each of the top models so we can choose the best one based on how much more probable it is than the other. Or if there's a number of models that are equally high probability, we can look at those collectively. We can either look at them individually, knowing their probabilities, or we can combine them, taking a weighted average of those top models based on their probabilities. So why would we want to do this? This gives us a better understanding of what might be important as a regressive variable. Right, in model selection, we either keep or reject. It's a binary decision, and it tends to make things look overconfident in how strong we are about the decision. In model averaging, we can compute probabilities that tell us how confident we can be in keeping or discarding some of our variables, and particularly when we're choosing between models that aren't nested. Also, model averaging can give us a more robust estimate of coefficients. So this is similar to shrinkage. Model averaging can be thought of as a shrinkage method. It does shrinkage, not the same way the other shrinkage methods do, but it gives you coefficients. And we take the average for each regressive variable, we take the average of the coefficients for the models, and we weight those coefficients by the probability of the model. So the coefficients are determined with the more probable models having more say in what those coefficient values should be. So before we start, a word of caution. Here on our plot, we have plotted from R on the horizontal axis shark attacks, and on the vertical axis ice cream sales. So this is some data called sharks that's available online for shark attacks. So we make a sharks model here, and we're going to do shark attacks as a function of ice cream sales. And here's what we get with our coefficients. You'll notice we have an estimated coefficients. Here's our standard things we get our output. There's a estimated coefficients in that column, and in this row we have the intercept, and in the second row we have ice cream sales. So the coefficient for ice cream sales is 0.33, coefficient for the intercept is 4.35. That sounds like ice cream sales might be a significant variable, and when we look here, the p-value for coefficients is 1.65 times 10 to the negative 7th. That's enormously significant. Of course, the point here is that while it's a significant variable in this prediction, if we want to predict shark attacks, we say that ice cream sales are a significant predictive variable, we don't want to say ice cream sales are causing shark attacks, right? The point here is causality versus correlation, right? Ice cream sales are correlated to shark attacks. They're not causing the shark attacks. So we have to be very careful how we talk about, how we think about predictive variables being significant or not, or included or rejected from the model. This, the data that this comes from, available online, it also includes population or number of people at the beaches, which have more to do with the shark attacks directly in causing or creating interactions between human and sharks that can lead to shark attacks than the ice cream sales. Ice cream sales are just a result of having a lot of number of people on the beach. So a good theme for the day, remember sharks and ice cream, meaning let's not confuse correlation with causality. Okay, so let's talk about Bayes' theorem. This is a somewhat simplified picture of Bayes' theorem, but Bayes' theorem essentially leads to this. It's a probability of event K occurring is equal to the likelihood of event K occurring divided by the sum of all overall possible events, the likelihood of events. And so this allows us to turn likelihoods, if we can measure likelihoods, we've talked about likelihoods before, we can turn them into probabilities. Combine this with the formula for likelihood for a linear regression model. The likelihood for a linear regression model in a Bayesian derivation is e raised to the negative BIC over 2. So what does that mean? That means if to do Bayesian model averaging, right? In Bayesian model averaging, we've said we want to compute a probability for each linear regression model. When we say a linear regression model, we mean our predictive variable, and we've chosen the explanatory variables or the predictive variables that are going to go into the model. So if we have a bunch of models, M0, M1 through MK, the probability of the ith model is equal to, right, probability of the ith model, this ratio here. It's the likelihood of that model divided by the likelihood of sum of the likelihoods of all the models that we're considering, which, if we use that formula from the previous page using BIC, turns into this. So it's e to the negative BIC for that model over 2, divided by the sum of e to the negative BIC over 2 for all the models that we're going to be considering. So since linear regression outputs BIC in a standard form, it makes doing Bayesian model averaging, meaning computing a probability for each of the models in consideration, quite easy. There's a number of, actually there's 3 packages that I know of that are good in R, and down on the bottom there's a link to a paper that covers those. And if that link's not good, of course, you can search around and find some review papers on those. What we're going to look at now is a classic Bayesian model averaging paper, which is the abstract is shown on the screen here from 1997. This is the kind of the era of Bayesian model averaging, kind of revolution time. What started to become popular because the math was developed and computers became fast enough to work effectively with Bayesian model averaging scheme around the same time. So here's the problem that we're going to cover in this paper. And so this problem in this data set comes from a 1973 work by Ehrlich called Crime and Punishment, and it's this question. How does the probability of imprisonment in jail affect crime rates? This is the type of thing that's important when you want to know how should we attribute money to pay for law enforcement, and what sorts of things do we want to attribute that money towards that are to decrease or control crime. And so some of the things you could think about is wanting to increase the probability of catching criminals, and the other thing you might want to think about is how long their time served should be, and how that will deter the criminals. And so the data, we have crime rates and 15 predictor variables for 50 states. And the predictor variables are this list right here, numbered 1 through 15. So for each state, we have the crime rate and the predictor variable for each of these. And I believe it's a crime rate in 1960 or 61. It's sometime around there. So you can look at each of these predictor variables, percentage of males in a certain range, indicator variable for southern states, mean years of schooling, police expenditure, labor force participation rate, sort of an unemployment rate, a bunch of other demographic variables coming down to wealth, income inequality, and down here at the bottom, probability of imprisonment and average time served. And the reason we're using 15 different predictor variables here to get this association is we want to control for all of these variables so we can predict really what's going on with the probability of imprisonment and average time served variable. So we can get those, the impact that's being caused or not caused. And this is, I said the bad word caused, and that's really what they're looking at. How much does those probability of imprisonment, average time served contribute to this? So effectively, that's what we're trying to do. When we do our analysis, we'll avoid using the word cause, but that's the underlying problem that they're trying to examine. Okay, so this is pre-Bayesian model averaging. Again, up here, we just have our restatement of our question and where this comes from. Over here, we just have our list of predictor variables. It's this table in the bottom of the screen that I care the most about. And this is doing model selection with methods pre-model averaging. And so we have 6 different models here. Each row corresponds to a different model. The first model is the full model, meaning we use all 15 predictor variables. The second model is one that's developed using stepwise regression. The third model is the model that's picked using the best Mallow CP score. The next model is the best model picked using the adjusted R squared, and then Ehrlich in his original paper had two models down there. And so in this middle section, we have a list of all the variables in each of the models. So if we work, for example, in stepwise regression uses variables 1, 3, 4, 9, 11, 13, and 14. Then we can look down, looking across the table, we get an R squared value for each model, the number of variables in each model, and then here we have the estimations for the coefficients that we care the most about, b hat 14 and b hat 15, and then the last column is the p-score for variable 15. Remember, variable 15 is that average time served in prison. And when we look at the coefficients, let's look at b hat 14 first. One of the things we find is we're getting coefficient values that range from negative 0.19 at the closest to 0 up to negative 0.45. And so there's a factor of 2 variation, right, in how much probability of imprisonment is decreasing crime rate based on these estimates, depending on which model you choose. And so, first conclusion, picking a different model, using a different method for picking a best model can give you widely different results in your estimated parameters. And if we look at b hat 15, b hat 15 is a much wider range. It can go from 0 in the stepwise regression model, threw it out completely, to Ehrlich's model 2 gave a value of negative 0.53, and his model 1 gave a value of negative 0.55. So, wide range in our coefficients based on which model is picked, and which model is picked is based on the model selection method. The other thing we have here is this P15. If you look at those, the P15 is the p-scores for variable 15, average time served. 3 of those tell us that that variable is significant, and 3 of us tell us that variable is not significant. All right, so we're getting significantly different results whether we optimize with Mallow-CP, adjusted R squared, stepwise regression, or the full model, or Ehrlich's model. Ehrlich picked his model with more subjective opinions and decisions on which variables should be considered. Okay, so this is pre-Bayesian model averaging. And what Bayesian model averaging it does is it searches through the models. For each model, it computes the probability that model is correct. And so here's the output for Bayesian model averaging. And there are 2 different search methods. Remember, we've talked about it's impossible generally to search through all possible models because the number of possible models is too big. And so this table we're looking at is using a search method called Occam's window. And it's some form of a stepwise regression type search, but I don't know the particulars that they used here, but it's similar to what we've talked about as stepwise regression hybrid methods. And so when we look at parameters, predictor variables 14 and 15 are the ones we care about. 14 is included in a lot of these models. 15 is not included in any of them, right? 15 is missing all the way down. This last column is the probability for each model. So the first model here, forgive my inaccuracy in drawing on the screen, but approximately there, includes predictor variables 1, 3, 4, 9, 11, 13, and 14, and its probability is 12.6. We see the next model, which varies only by not including number 9, has a probability of 9. So that's only slightly less probable. And the model after that has a probability of 8.4 and then 8, and they're slightly different, excluding or including some different variables. So what we see from the top, there's not a drastic difference in likelihood in the top model. So there's a couple of models here that are worth considering, that should be considered. It's a fallacy to say we're confident it's that top model and not the second and not the third. They all are worth considering. One of the ways we can measure the goodness for a linear regression model is something called performance comparison. Is a performance comparison using predictive coverage. And here's the definition of predictive coverage. It's the percentage of observations in the performance set that fall in the 90% prediction interval. So 90% of the states, well, say this correctly, This tells us for the model averaging, 80% of states fell within the 90% prediction interval for model averaging. These are our two different methods, MC cubed, that's a Monte Carlo method, and Occam's window. They're for different methods for searching through the models, and they give us better predictive coverage than all the other methods down below. A number of methods using adjusted R squared and CP. This is the probability of being included in the top model for the two variables, well, for every variable. Here's the 13 variables that we're trying to control for, and there are two variables, 14 and 15, here in the end. This Occam's window and MC cubed, remember those are our two different search methods, and we see that the probability of imprisonment, the probability that should be in the model is 83, or 0.83, and the probability for MC cubed, the probability we get from using the MC cubed search, is 83. So that's a very high probability. So probability of imprisonment is, with high probability, having an impact on crime rates. Average time searched in prison, we get either 0 or 22, depending on which search method we use. So lower probability, you can derive how you want to phrase that. Maybe the average time served in prison has an impact, or maybe not. Yep, and just to recap, the probability here, when we say this probability is 83, we go back and we look at all of the models. I went back 2 slides in this chart, all the models that include regressive variable 14, and then we look at the probability for regressive variable 14. Because that model includes 14, we add up the probability for every model that includes regressive variable 14, and that's the probability that regressive variable 14 should be included in the model. So that's what 83 tells us. There are some different packages in R, and so here's the output from these 3 different packages, BMS, BAS, and BMA. And we have the probability for each of the different factors. And so we see income inequality has the highest probability for being important in prediction of crime rates, and then education. And then third on the list out of all of our predictive variables is imprisonment probability. So that tells us that imprisonment probability has a strong impact on crime rates. You could infer that criminals looking at, and this is a debated inference, looking at doing crime and saying, hey, I'm more likely to get imprisonment, so I'm less likely to commit the crime. But that's a little bit of the inference that's outside of the statistics that we're trying to look at and evaluate accurately. Here we go down the list to time right here, and we see the probability that should be included is in the 0.33 to 0.44 range, depending on which package you've used. So this is giving us a more robust picture of which variables should be included in our linear regression. All right, this Bayesian model averaging methods are finding applications in a lot of areas. They're good in very important economic prediction, like we're looking at here in weather forecasting. I know at the University of Virginia, there's recently a project trying to predict sepsis in patients. I think it was sepsis, I'm not sure, predicting health concerns in patients. And they used Bayesian model averaging to determine what the best predictive variables are, and then used a decision tree, which we'll talk about in a later module, to do the prediction. But the regressive variables that were picked for that decision tree were picked with model averaging. The decision tree was used not because it's the most accurate, but it's because it's what medical people are used to using for making decisions about patients. And now I want to look at another example of using multivariate linear regression for prediction and statistical inference. It's similar to what we've been doing. And in this example, there's 2 reasons I picked this example that I want us to take a short look at. One reason that I picked this is because this is an example that's similar to things that we've been using and that we're going to look at in the lab. Specifically, we've been using the hitters data set where we're predicting baseball players' salaries based on a number of underlying factors and trying to figure out the best methods for predicting salary. So that's the first reason. This is a real-world important application that's similar to something we've been doing in the class. Second reason is this is a politically charged, emotional topic. One, a lot of people have a lot of interest in nuancing one way or another. And when I say that, I don't mean that to criticize people. People have strongly held beliefs that make them want things to be one way or another. And so just to be clear, when I'm talking about this, I'm not making any recommendations or statements other than the fact that we need to examine things rigorously with proper statistics and proper linear regression models and predictive analytics methods when we make decisions and statistical inference. And so in this example, we're looking at the gender wage gap. So this is the gap that men on average get paid more than women on average. And the question, there's an important underlying question, what contributes to this? What are the most important factors? Certainly everybody I know doesn't want men to get paid on average more than women for the same job in the same situations, all other things being held equal. That is a bad thing. We would like that pay to be different. And the question is what things are contributing to that. And so this is one paper doing a research study trying to understand what factors contribute to that. And we have to take a look at any study like this. You have to look at what their data is. And so they're using this 2013 wage data from Household and Income and Labor Dynamics in Australia. This survey, so this is a survey from one data set they're examining, not the universe as a whole. You can, extend maybe from this to a general things, or maybe not. More from, repeated studies you can extend general, not from one study. But their result, they're looking at personality and pay. And do gender gaps in confidence explain gender gaps in wages? And gender gaps in confidence means the difference in emotional factors, personality traits, and in particular, they're looking at confidence as a personality trait. So men and women have statistically measurable differences in confidence in this data set. And do those differences in confidence, do they explain the gender wage gaps in wages? So does those differences in confidence really, well, they say, do they explain? Let's look at their actual conclusion in their abstract. And what we have here is the abstract. They say they use a different method for going through the linear regression, and they're evaluating a number of the top models and comparing them to figure out what input factors are important and how much they impact the results. They say reveals that men's stronger hope for success, they give a couple of personality traits. Lower fear of failure and lower agreeableness contribute to the gender wage gap. They don't say whether it explains it entirely or not, but they contribute to the gender wage gap. And that women's higher level of conscientious is the only trait that serves to narrow that gap. So what they're looking at is some of these personality traits are contributing to the gender wage gap, and they're important traits when you're trying to understand what are the factors that create the gender wage gap. Now, when I say create, I'm trying to avoid the word causality or cause, but really we need to do the statistics properly, but a lot of people will extend it to what are the things that we need to control to reduce the gender wage gap. So if you have to make decisions on how to reduce gap in wages, it's based on gender alone, you need to understand the other factors as well as wages that are caused by gender. And here's a table from the paper, and what you see very similar to the things we've been doing. They take a number of different models. Here's model 1, down the side of the traits. You can see the way the different coefficients are measured and whether they're significant or not. In model 2, here's model 3, model 4. The big 5 only refers to different factors, personality factors. And so just recap here, this is a study evaluating something important, something a lot of people have an interest in seeing done well. People have a tendency to want these results to look one way or another based on personal philosophy or possibly getting paid, right? A company that has to do a lot of restructuring based on gender wage gap. There may be some pressure to keep costs down, to measure that gap as being lower. There may be pressures for other people to try to measure that gap higher. We all have our personal philosophies. It may make us want it to be one way or another. And so my point in bringing this example up is to say we need to do the statistics rigorously and consider all the underlying traits for things that are really important. I want you to be able to do good data mining, linear prediction, linear multivariate regression, even in situations where there may be influence, personal factors or pressures, or somebody paying you to try to get it to be one way or another without even actually saying that. And I would like you to be able to do as well at being objective as you can, and at least making sure that the statistics are done well. And I'm not saying this paper is conclusive or isn't, or is right or is wrong, other than the fact that they are considering these personality traits as part of something that's important. Okay, now I would like to take a look at another application specifically of Bayesian model averaging in some software I wrote for one of my companies that we sell. And so the software analyzes images, identifies specific chemical bonds present in pixels in the image, and then does Bayesian model averaging to figure out what materials are causing, and in this case we do mean causing because we're examining the underlying physics, the observed light, measured light in the specific pixels. And then the output is output in the form of an HTML web page, and that model averaging allows us to present probabilities to people who aren't experts in the field, but most people understand probabilities well. And so you'll see that when you see the output, which we'll look at in a moment, that it can be understandable or interpretable to a non-expert, which is another advantage of the model averaging approach. Okay, so here's the output from the software. The software is called Ninja. And the way this works, this side here, we have an image that's been collected over Washington, D.C. You might recognize the mall through here, the Capitol building there, and let's see, Washington Monument, and the White House over in this area. So this image was collected by a NASA aircraft at, I think, about 50,000 feet up, so it's about 10 miles, looking at materials on the ground, and this image was collected in a special sensor called a hyperspectral sensor. So instead of collecting just 3 visual colors, we see red, green, blue, it collects hundreds of colors, and you can do chemical analysis on the materials on the ground. And so this is a list of all the materials that have been found. This is looking for polymers, and we can switch over and see all of the detections, the places of the polymers that we're looking at have been found. And just as a quick example, we're going to pull up this. It's a HDPE, that's a high density polyethylene polymer. And this shows that we found the polymer right in that location. So here's a running track, and there's something made of polymer. Their polymer is a plastic. These plots show us some of the spectroscopy that's done to determine those polymers. The thing that I care about at the moment for our purposes is this table. So this is a table of explanatory variables that are going into the regression models to try to determine what material is here on the ground. And so the light that's collected for these 2 pixels is coming off a mixture of materials. And so we do linear regression to figure out what mixture of materials there are. And what this is telling us is that the polymer HDPE that we care about, when we do lots and lots of linear regression models, using Bayesian model averaging, the probability for these HDPEs is given here, 0.31, 0.16, 0.14 for each of these individual variables, and the net probability from our Bayesian model averaging is 1.00. This is telling us it's a very high probability that we have HDPE, which is high density polyethylene, at this location on the ground. High density polyethylene is used for outdoor plastics, furniture, garbage cans, things like that. And this data has GIS associated with it, so we can click on the Google Earth link. That will open up Google Earth in this location. And you can see here's that track that we're looking at, and the polymers are located just up and to the left of that track. And so we are finding these plastic slides that are on this playground equipment using the software from 5 miles up in that NASA imagery, searching all of Washington, D.C. So again, the Bayesian model averaging determines these probabilities which determine the net probability this polymer is present at this location. Okay, so in review, we've talked about Bayesian model averaging and Bayesian model selection or probabilistic model selection. And in Bayesian model averaging, instead of picking a single best model, we compute the probability for the top models. And that allows us to look across the top models and figure out which ones are really good, which ones are also worth considering. Why do we do this? It gives a better understanding of what explanatory variables or what regressive variables might be important, instead of making an overconfident decision of what we should just keep or discard. It also can give us a more robust estimate of coefficients, and we can think of that as similar to shrinkage. The coefficients that only come up in linear mixture models that have a low probability wind up with coefficients that are decreased because of those weighting the averages with those probabilities. Thank you very much.